My name is Ben Brock. I'm a postdoc in Michel Devry's lab at Yale University, and I'm excited to tell you about our work on realizing error-corrected logical qudits, d greater than 2. Before getting started, I just want to thank the team I worked with on this project, in particular Alec Eichbusch, Vlad Sivak, Andy Ding, Luigi Frunzio, my advisor Michel Devry, and our theory collaborators Shraddha Singh and Steve Gervin. So I like to motivate this work from the perspective that Hilbert space dimension should be considered a resource for quantum information processing. This is clearly true for quantum error correction, where a large Hilbert space is necessary to redundantly encode our quantum information. But there are also many examples of qubit gates that can benefit from having access to levels beyond the computational manifold. And finally, the use of qudits, or d-level quantum systems, as the fundamental unit of quantum information has many promising applications, which is what brings us all together this week. A couple of examples is they can enable the efficient compilation of quantum algorithms, as well as the efficient simulation of quantum systems that are more naturally framed in terms of qudits. For these reasons, there's been a lot of experimental effort put forward to realize qudit-based platforms for quantum computing. But to really deliver on the promise of these qudits beyond the NISQ era, quantum error correction is going to be necessary. So today, I'm going to present, to the best of my knowledge, the first experimental demonstration of error-corrected logical qudits with d greater than 2 using the Gottesman-Kitaev-Preskill bosonic code in a circuit QED architecture. So I'll begin by reviewing how quantum error correction of GKP qubits works, and then how we extend this to the case of qudits with d greater than 2. For the GKP qutrit in d equals 3 and the ququart in d equals 4, we've been able to demonstrate beyond break-even error correction, meaning that our logical qudit lives longer than the best physical qudit available in our hardware. So the idea of these bosonic codes really follows in the same vein of using Hilbert space dimension as a resource, in this case using the large, formally infinite dimensional Hilbert space of a harmonic oscillator to encode a logical qubit. The goal being that physical errors on our oscillator should map our code space to an orthogonal error space that we can hope to recover from without corrupting our quantum information. So here are 3 examples of bosonic codes: the cat code, the binomial code, and the GKP code. And here are plotted the Wigner functions of the maximally mixed states of these bosonic codes, which really serves as their fingerprint, kind of telling us how quantum information is delocalized in phase space. And there's been a lot of experimental progress toward realizing these codes, and in fact, all 3 have reached or exceeded the break-even point in circuit QED architectures. But my focus today is going to be on this GKP code, particularly because it admits a very simple extension to the case of qudits with d greater than 2. So great. So first, the case of the qubit, though. So the code words of the ideal GKP code are lattices of position eigenstates with the plus c state centered at 0 and the minus c state centered at square root of pi. We can see that both states are invariant under a displacement in position by 2 root pi, which is the x stabilizer of the code. And we can see that if we apply a displacement of root pi in position, we flip the plus c state to the minus c state and vice versa. And this is the logical x operator of the code. We can see the other operators of the code most straightforwardly by looking at these code words in momentum space by taking the Fourier transform. And we see that they are, again, grids of momentum eigenstates. And here we can see that they are also invariant under displacements of 2 root pi in momentum. But when we apply a displacement of root pi in momentum, the plus c state is invariant, but the minus c state picks up a -1 sign. So this is the logical Pauli z operator of the code. The structure of this code really comes from the geometric phase associated with displacements in phase space. That is that 2 displacements commute up to a phase given by the area they enclose. So in particular, in order for these two stabilizers to commute and have a common eigenspace, the code space, they have to enclose an area that's an integer multiple of 2 pi, and it turns out that this integer multiple sets the dimension of the code space. In addition, these Pauli operators have to anti-commute, and we can see that that requires them to enclose an area of pi in phase space. Great, so that's all well and good, but these ideal code words consisting of infinitely squeezed peaks extending out to infinite energy are obviously not physical. So we instead, in practice, work with the finite energy code words, which are obtained by applying a Gaussian envelope to both the states and the operators. And this delta parameter sets both the overall envelope size as well as the squeezing of the individual peaks. And the Wigner functions of these code words are, again, squeezed peaks of positive and negative sign in phase space. For those unfamiliar with the Wigner function, it's a phase space representation of the state of the oscillator, as good as the wave function, where position is on the x-axis of this phase space and momentum is on the y-axis. And the key feature important for this talk is that if you integrate the Wigner function along a given axis, what you get out is the marginal probability distribution of the oscillator with respect to the orthogonal axis. And this is a convenient way of visualizing the direction in phase space along which quantum information is encoded in these states. So we see that if we integrate these states with respect to momentum, then the alternating peaks destructively interfere, and the uniform sets of peaks constructively interfere, and we get these resulting probability distributions for the plus C and minus C state that are disjoint. And this disjointedness is precisely what gives the GKP code its resilience against small displacement errors. The idea is that if the oscillator undergoes a small unknown displacement error, these states can still be distinguished based on whether they are closer to 0 mod 2 root pi or root pi mod 2 root pi. And these small displacement errors are exactly what the GKP code was originally designed to correct for. So consider an error state where we take the GKP code words and displace them by a small unknown amount delta in position. If we apply the Z stabilizer to this error state, we get back a phase that encodes the value of this displacement error. So the question becomes, how do we measure this phase of a displacement operator to extract this error syndrome? Well, one answer is to use an ancilla qubit and perform a conditional displacement gate that admits two interpretations. The most straightforward is that we are displacing the oscillator in one direction or the other, depending on the state of the ancilla. And the other perspective is that the ancilla undergoes a rotation around its z-axis, depending on the expectation value of the displacement operator in the oscillator. And from this interpretation, for this circuit, we can see that if we prepare the ancilla qubit in the plus state and perform this conditional displacement, then if we measure the ancilla afterwards along its equator, we can get some information about the expectation value of this displacement operator. So for the particular case of the Z stabilizer, if we perform this conditional displacement of a Z stabilizer length, then our error that we hope to extract is encoded along the y-axis of the ancilla. In particular, if this displacement error is in the positive direction, we're more likely to measure the ancilla in the plus y state. If the error is in the negative direction, we're more likely to measure the minus y state. So after this measurement, along the y-axis of the ancilla, we can give the oscillator a kickback in the opposite direction, thereby mitigating the effect of these errors. And the way to view this error correction protocol procedure is really as a biased random walk, that if we start to get errors bringing us to the right, we start getting much more likely to give kicks back in the opposite direction, and vice versa. So we're preventing these small displacement errors from accumulating into large ones that would corrupt our information. In particular, if we accumulate a displacement error of root pi that's unknown, we have a logical error. So this is all designed for the finite energy, for the ideal code but it can be adapted to the finite energy code with a slightly more complicated circuit, but again, just consisting of conditional displacements and ancilla rotations. And here the nomenclature SBS, or small, big, small, refers to the amplitude of these conditional displacements. The small amplitude, epsilon, encodes the envelope size, and the big amplitude of 2 root pi encodes the stabilizer length. We can also use this conditional displacement to perform logical readout of our GKP qubit with the ancilla. So here, the idea being that displacements give us the logical Pauli operators, so the conditional versions of them are intuitively CX and CZ operators. And we can use this circuit to really imprint or really entangle the ancilla x-axis with the logical z information of our GKP qubit, such that a subsequent measurement of the ancilla along its x-axis also constitutes a projective measurement of the GKP qubit along its z-axis. In our lab's GKP experiments so far, we have used a transmon as an ancilla. The transmon is fabricated on a sapphire chip, consists of a Josephson junction between 2 large pads that form its shunt capacitance. And when we insert it into this 3D microwave cavity, whose fundamental mode we use as our oscillator mode, the dipole interaction between the two gives rise to this dispersive interaction, where the oscillator frequency depends on the state of the transmon qubit. And in particular, this interaction provides the nonlinearity necessary for universal control of the system, so that with appropriately engineered drives on the transmon and the cavity, we can realize this conditional displacement gate necessary for all of these GKP operations. So in this paper from our group last year, we were able to use this architecture to realize beyond break-even error correction of a GKP qubit. And this involved optimizing several aspects of the experiment, but I want to tell you about or highlight 2 in particular. First, instead of fixing these experiments, these parameters of our error correction protocol based on our theoretical model, we allowed the majority of them to be free parameters, 45 in all, and we used a reinforcement learning agent interacting directly with our experiment to optimize our quantum error correction protocol over these 45 parameters in situ. We also fabricated a state-of-the-art tantalum transmon following the recipe developed at Princeton. And this transmon has a T1 of about 300 microseconds and a T2 echo of 240 microseconds. And the cavity in this case has a T1 of 610 microseconds and a T2 of 950 microseconds. And with this device and our optimized protocol, we were able to achieve an error-corrected GKP qubit with x and z lifetimes of 2.2 milliseconds and a y lifetime of 1.3 milliseconds, all significantly larger than the best lifetime of the best physical qubit available in our system, which is the cavity Fock qubit consisting of the 0 and 1 photon states. So put differently, this is really saying by encoding quantum information in these very complicated states of light and performing measurements and feedback operations on them constantly, we're able to prolong the lifetime of our quantum information to a lifetime almost more than twice as long as the lifetime of a single photon in that same oscillator. And this is really showing that quantum error correction works. We're able to encode our quantum information redundantly and perform these syndrome measurements to prolong the lifetime of our quantum information and prevent these physical errors from accumulating into logical ones. And I just want to mention here also that this same experimental device is the device I used for all of the experiments on qudits that I'll be showing now. So next, I want to discuss how this GKP code extends to qudits with dimension d greater than 2. So it's actually fairly straightforward. As I mentioned, the structure of the GKP code comes from the geometric phase associated with these displacements. That is that 2 of them commute up to a phase given by the area they enclose. So in order for these stabilizers to commute, they have to enclose an area that's an integer multiple of 2 pi. And this integer multiple d sets the dimension of the code space. And these code words of the GKP qudit are again grids of position eigenstates. But here we can see that the characteristic lattice spacing has grown. It's scaled to be larger, to be root 2 pi d. And on the other hand, the spacing between our code words has shrunk by root d, and it's now root 2 pi over d. The logical operators on our code are now the generalized Pauli operators, also called the clock and shift operators, where they are realized by displacements of root 2 pi over d in either position or momentum. The generalized x operator increments our states by 1 mod d, and the generalized z operator, acting on the nth eigenstate, returns the primitive dth root of unity to the nth power. And these operators now obey this generalized commutation relation based on the area they enclose in phase space. So again, these ideal code words are not realizable in the lab, so we have to use the finite energy versions of them. And here, for an example, are the finite energy code words of the GKP qutrit in d equals 3. And the take-home message here is really that the qdit code words, at least in the z basis, look just like the qbit code words. There are just more of them. The characteristic lattice spacing has grown, and the spacing between states has shrunk. So to generalize our error correction protocol, remember that this stabilization protocol, the stabilizer length, is encoded in this big initial displacement amplitude, which we now want to make commensurate with the qdit lattice spacing, which is root 2 pi d. And as I said, or maybe I didn't say, this quantum error correction protocol, you'll notice that there aren't really actually feedback operations here, and it is autonomous, requiring us just to reset the ancilla qubit at the end. And in this sense, it can really be viewed as an engineered dissipation onto the finite energy GKP code space. And from this perspective, if we start with the cavity in vacuum and apply the stabilization protocol 200 times, we should cool to this maximally mixed state of the GKP qudit. And that's exactly what we find experimentally. So here, showing you experimental data for the characteristic function measured at the end of this process, where the characteristic function is defined as the expectation value of the displacement operator. And for these mixed states, we expect them just to have bright spots at the lattice spacing of the GKP code. And we see that this lattice spacing grows as root 2 pi d, just as we expect, for d equals 1 through d equals 6 here. So we're able to stabilize the maximally mixed GKP code space and stabilize the GKP qudit manifold. Before getting into our other experiments, I also want to discuss what exactly we mean by break-even, and especially how this generalizes to qudits. So to quantify our error correction protocol for a metric for how good it is, we turn to the average channel fidelity, which is a metric for comparing how well a given channel approximates its target. In this case, we're wondering how our error correction channel E approximates the identity operation. So in general, this is going to evolve in a very complicated way in time, but we can always expand it to short times and associate with it a single decay rate, gamma effective. And here this prefactor comes from comparing it to a depolarizing channel on a qudit, which takes probability out of the density matrix at rate little gamma and deposits it into the maximally mixed state. So we now have a single characteristic rate characterizing our error correction protocol, characterizing effectively the decay of our error correction channel of our system. And this allows us to compare on equal footing two different systems that may have very different qualitative decay channels. In particular, we're interested in comparing our best physical system to our error-corrected logical system. And this gives us a notion of quantum error correction gain. And when this is unity, we said we've reached the break-even point. So that's great, but as an experimentalist, this is not really something conducive. This expression in terms of a unitary operator basis isn't really conducive to performing measurements, so it requires a bit of massaging. So for d equals 2, we use as an operator basis the Pauli operators. And this expression simplifies into this form, written as a summation over both eigenstates of the three cardinal Pauli operators, x, y, and z, Here I've written y as xz, because it'll need generalizing to qudits. And this expression inside the summation, this term, is now something I can experimentally measure. It corresponds to preparing a given Pauli eigenstate, performing error correction, and measuring the probability that I remain in that same state. And the effective depolarization rate of our logical qubit in this case can be written as an average over the decay rates of each of these cardinal Pauli directions. And this diagram on the right is meant to represent the Pauli group in D equal 2, where there are these 3 cardinal directions we can move in with periodic boundary conditions. It's kind of trivial in D equals 2, since you move twice in a given direction and you get back to the identity. But in D equals 3, there's a bit more structure, where we can now lay it out on a 3x3 grid with periodic boundary conditions, and we see that there are these 4 independent directions that we move in to hit all of our operators without overlap. We have the x direction, the z direction, the xz direction, and now this x squared z direction. And if we diagonalize in these 4 kind of characteristic cardinal bases, we're able to simplify the average channel fidelity into this form, where again, this is a term I can experimentally measure. And it's kind of giving us a prescription for the measurements we have to do to fully characterize our error correction protocol, which is we have to prepare all 3 eigenstates of all 4 of these cardinal Pauli operators. And we get this nice form for the effective depolarization rate of our logical qutrit. That's just an average over the decay rates of these 4 cardinal Pauli axes. For the ququart, things get more complicated. There are now 2 additional directions we can move, and we see that we have overlaps here. That is, we can arrive at a given operator by moving in 2 different directions. And if we try to straightforwardly write down the average channel fidelity, using the similar form as the previous case of d equals 2 and d equals 3, we actually end up double counting these 3 operators. Conveniently, all 3 of these operators actually commute with one another, so they could be simultaneously diagonalized in what I call the ququart parity basis, where the ququart can be viewed as having 2 bits of parity, one x-like bit associated with the eigenvalue of x squared, and one z-like bit associated with the eigenvalue of the z squared operator. So now the prescription is a bit different. We need to subtract off the double counting due to these operators. So we get this more complicated form of the average channel fidelity, where we now have to prepare all 4 cardinal Pauli eigenstates of all 6 of these cardinal Pauli directions, as well as this parity basis, and we need to be able to perform measurements in all of these bases. But that's kind of the prescription for the experiments. And we get this form of the effective depolarization rate. That's the sum of all of these rates, subtracting out the decay rate associated with the parity basis, similar to the form we get here. Great, so next I want to tell you about our experiments and realizing a beyond break-even error-corrected logical qutrit. So state preparation is actually fairly straightforward, since we have universal control of our oscillator by interleaving sequences of qubit rotations and conditional displacements. So in particular, we want to optimize for the unitary that brings us from our cavity from the vacuum state to our desired Pauli eigenstate that we need to prepare. And we could perform this optimization over all of these parameters, theta n and phi n and beta n offline, and then play the resulting pulses we get on our experiments and perform Wigner tomography to verify that we are indeed preparing the desired Pauli eigenstates. And here we have a bit more structure in the different directions along which quantum information is encoded in this higher dimensional system. The x basis is oriented horizontally, the z basis vertically, the xz basis diagonally, and the x squared z basis is along this other diagonal, which one way of viewing this is from the fact that x now in the qutrit cubes to the identity. So going to the right 2 is the same as going back 1 with the x inverse operation. The real challenge with this experiment was actually coming up with a circuit using just controlled Pauli operators and qubit rotations that enables us to read out the state of a logical qutrit using an ancilla qubit. So this was actually a highly non-trivial circuit to come up with. If anyone has any ideas on generalizing this to arbitrary prime dimensions, be very interested to discuss. But this is the circuit I came up with for performing this measurement, and it requires kind of asymmetrically splitting the Hilbert space up. So the strategy of this circuit is to entangle the plus x state of the transmon with the 0 state of the qutrit, and the minus x state of the transmon with the entire 1,2 subspace of the qutrit, such that measurement of the qutrit along its x-axis collapses the qutrit. Sorry, measurement of the ancilla qubit along its x-axis collapses the qutrit accordingly. So if we measure 0 here, we're done. But if we measure we're in the 1,2 subspace, we perform another similar circuit that distinguishes between the 1 and the 2 states. So to verify that this circuit is indeed performing the projective measurement we wanted to, we prepare the cavity in the maximally mixed state of the qutrit, perform this measurement sequence, and perform Wigner tomography at the end of the line, post-selected on our various measurement outcomes. And we see that indeed, when we get 0, we are preparing the 0 state centered at 0. The 1 state is offset by root 2 pi over 3, and the 2 state is offset by root 2 pi over 3, exactly as we expect. And I should note here that there's nothing really special about measuring in the z-axis. You can measure in any Pauli axis by simply adjusting the length and direction of these conditional displacements. So as in our experiment with qubits, we're now able to perform state preparation, error correction, and logical measurement in an arbitrary Pauli basis. So we again optimize our error correction protocol using a reinforcement learning agent, and we characterize all 12 measurements we have to perform to fully characterize our error correction protocol of the qutrit, and we find x and z lifetimes of a little over 1.1 milliseconds, and diagonal xz and x squared z lifetimes of about 730 microseconds for our optimum protocol. And this gives us an effective depolarization lifetime of 886 microseconds, which we can compare to the best physical qutrit available in our system, which is the cavity Fock qutrit consisting of the 0, 1, and 2 photon states in the cavity. And that has an effective lifetime of 488 microseconds, giving us an error correction gain of 1.82, well beyond break-even. So next, I want to briefly go through, in the interest of time, our experimental results on the ququart, but it essentially follows the same basic logic. We are going to have to prepare now 28 different states, perform measurements in 7 different bases, and optimize the quantum error correction protocol. So there's nothing different in the methodology for state preparation. We're just optimizing different unitaries that bring us to different states. And here we prepared all 4 eigenstates of these 6 Pauli operators, as well as all the eigenstates in the parity basis. And we can see that there's more richness to the structure of this GKP code in higher dimensions. There's kind of more directions and phase space along which we can encode quantum information. The measurement of these Pauli measurements of the ququart are actually more straightforward than the case of the qutrit, because with our qubit measurements with an ancilla qubit, we have kind of a binary measurement that can split the Hilbert space in 2 symmetrically. So here, to measure in the z basis, Okay, there we go. To measure in the z basis, we perform the CZ squared operation that distinguishes between the even and odd subspaces of the ququart, and then a subsequent measurement that distinguishes between the last 2 possible states. And we again see that we're able to verify that we are performing this projective measurement in the Pauli basis, and this extends to arbitrary Pauli bases of the ququart. And similarly, we can measure in this ququart parity basis that I mentioned. And we find an optimized error correction protocol with these x and z lifetimes of a shorter duration of 860, 870 microseconds. So we're incurring some overhead here as we go to higher dimensions, for sure. And then these diagonal lifetimes of 520, 530 microseconds, and a slightly longer lifetime of the parity basis. And one thing I want to mention here that's interesting about this ququart, it didn't mention with the qutrit, but there was a symmetry to the way a state decayed at equal rates into the other two states for the qutrit. And we could see that that's not the case here. There's some structure to the way that physical errors propagate as logical errors that could be useful for another layer of error correction. The overall lifetime we get for this ququart is now 620 microseconds, and we can compare it to our cavity Sivak ququart, which has a lifetime of 330 microseconds, giving us a quantum error correction gain of 1.7, also well beyond break-even. So to sum up, I've shown you the first realization of error-corrected logical qudits with d greater than 2. And we've been able to achieve, it's not just the first demonstration, it's also a useful demonstration in that our error-corrected logical qudits are able to live longer than the best physical qudit available in our hardware. And beyond these particular demonstrations, what I really like about this project is it kind of demonstrates by example that the Hilbert space of the oscillator really is a very big place with lots of room left to explore. And thank you for your attention.